astrophysicists. I'm excited. There we are. Hello, everyone. I'm excited today to have Professor Stephen Taylor with us from Vanderbilt. Evidently, you all are too, because dinner filled up real fast. So sorry about that. Professor Taylor got to the University of Cambridge before taking 2 postdoctoral fellowships in much sunnier Pasadena. With NASA and then Nanograph, he since traded the weather for real trees, like we have around here, taking a position professor of physics and astronomy at Vanderbilt. His interests lie in gravitational wave astrophysics and data analysis. And today we're talking about finding supermassive black hole binaries, gravity and light. Right, take it away. Literally.
Oh, I guess it wasn't switched on. It'll be a treat. They can find out.
I think it's for this.
Yeah. All right. Thank you very much, Ben. Hopefully this is coming through okay. It was interesting to hear my career described in terms of the geography and my choices based on the sunlight, which, I mean, coming from the UK, it helps. Welcome, everyone. Hopefully today I'll give you an idea of the kinds of gravitational wave searches that we're doing in pulsar timing array science. This is at very, very low frequencies in the gravitational wave spectrum. And not only the recent searches that we've done, but the targets that we hope will be in the near future for pulsar timing arrays as well. So just to orient everyone, Ben said it's a very diverse black hole crowd, but not too many people working on gravitational wave observations, actually. And so the gravitational wave observations with which most people are familiar are at higher frequencies or short timescales here. We've got merging stellar mass black holes, neutron stars, and combinations thereof. Then at lower frequencies, you're accessing more massive black hole coalescences, and that'll be the regime of the LISA detector, hopefully launched in 2035. I'll talk more about that soon, fingers crossed. And then at lower frequencies, where you're at orbital periods of your massive black holes of years to decades, you've got binary supermassive black hole in spirals accessed by pulsar timing arrays. And then if you're familiar at all with the characteristic strain spectrum of gravitational waves, this is another way of viewing things where you've got LIGO and Virgo and Cagra up here with stellar mass compact binary in spirals. Then really lots of different types of sources at millihertz frequencies, where you'll have not only massive black hole coalescences, but also almost every ultra compact binary system in the Milky Way, along with exotic systems like extreme mass ratio in spiral events. And then at the lower frequencies, where you're seeing the sensitivity curve here of nanograv and then a near future international pulsar timing array data set, you've got supermassive black hole binary in spirals, likely manifesting as a stochastic background of gravitational waves, because we don't have the resolving power to pick out all of these individual systems at the same time. Now with that, giving you an overview of the gravitational wave landscape, let me try to do PTA's justice in one slide so we can move on to some of the science. This is essentially one gigantic Doppler ranging experiment, except we're using pulsars in the galaxy as the other end of our experiment. And obviously we're using millisecond period pulsars in this case because they're very stable. They tend to be stable rotators compared to canonical pulsars that were first discovered. They have lower amounts of intrinsic timing instability than canonical pulsars. And we're using these because every time the pulsar rotates its beam into our line of sight, we can measure a radio pulse and get an extraordinarily constructed model of when those pulses should arrive over long time scales. So with these as our clocks in space, if we track a highly exaggerated gravitational wave moving into our galaxy, we wish it was like that, it intersects the Earth pulsar line of sight, and we get these pulses arriving a little bit earlier or a little bit later than expected. And so we're looking at these timing offsets or timing residuals for the presence and influence of gravitational waves. Now, unfortunately, not even our most extraordinary and well-timed pulsar would be useful if we were only doing this with one pulsar, because there are lots of intrinsic sources of noise and instability in pulsars, even these millisecond period pulsars. So we can't just do it with one pulsar. The gravitational wave signal, its spectral properties would look very similar to just intrinsic noise instabilities. So instead, we rely on using arrays of millisecond period pulsars. And
what is the biggest noise source for the pulsar?
It's the fact that they tend to have intrinsic rotational instabilities, and the physics of that is not very well constrained at the moment. So they're fairly stable rotators, but they do show long timescale stochastic drift in their rotations. Coupled with that, you've also got the physics of the interstellar medium that we try to characterize, but these are radio pulses propagating through all of that ionized interstellar medium, and that contributes to source of noise as well. We have to observe over several different radio frequencies in order to try to disentangle that from the actual gravitational wave signal and even the intrinsic pulsar noise. So if we're using, say here, 3 pulsars, and now we're not just looking at one gravitational wave signal, but in fact, a background of gravitational waves, all impinging upon these different 3 pulsars. Because this is a superposition of now gravitational wave effects in these 3 different pulsars, you're certainly not getting the nice chirping, in-spiraling signals that you see in reconstructions from LIGO. This is, for all intents and purposes, a random process, but all is not lost because these random time series, these random gravitational wave strains, are statistically correlated across the 3 different pulsars and all the pulsars that we can monitor. And the statistical correlation signature for an isotropic background of gravitational waves only depends on the angle of separation between the pulsars in the sky, and it's got this famous for us signature known as the Hellions and Downs curve. So what this is telling us is that if we take the same pulsar, correlate with itself, it'll give us obviously a correlation signature of 1. But as soon as we look at a slightly different pulsar, separated from that initial pulsar by a gravitational wavelength, then the correlation drops to 1/2. It's because, as I'll talk about this later, but only half of the gravitational wave effect is actually correlated amongst the pulsars if they're slightly offset. Question?
Is there some physical intuition towards this curve?
Yeah.
You do those calculations, and somehow the integral would just drop out. Integrating controls, I don't like.
There is some physical intuition I can give. So just to give a brief explanation, so what we're doing is we're taking pulsars and we're separating them on the sky, and the gravitational wave background causes the timing residuals in those pulsars to decorrelate, become negatively correlated, and then positively correlated again, but not at the same level as we had before at low angular separations. So it is quadrupolar-ish because the gravitational wave antenna response pattern is mostly quadrupolar. However, the pulsar timing gravitational wave antenna response pattern is not entirely quadrupolar. There's actually a preferred direction. And so we're most sensitive, according to that antenna response pattern, to gravitational waves that are coming from the same direction as the pulsars in the sky. So we tend to be more sensitive when we've got pulsars close together in the sky, and in an ensemble sense, integrating over the entire sky, we get a greater correlation there. And if you're interested, later on, I'll give a graphic for how I'll reconstruct this Hellions and Downs curve. So this is the important correlation signature that we sit at the center of all of our detection statistics. So when we're looking at evidence for gravitational waves, we're trying to find evidence initially of a statistically isotropic background. There are lots of collaborations that are doing this kind of gravitational wave science. So I'm the chair of the NanoGrav collaboration, which uses these different radio telescopes to monitor arrays of pulsars. Obviously, we're not using Arecibo anymore, but it's a very important legacy component to our data sets, even still, because we're looking at gravitational wave signals that vary over years to decades. And so that data is still very important. There's the European pulsar-timing array, where I got my start as a PhD student. And then PARCS is also a legacy collaboration in Australia doing this. And then newer collaborations including the Indian pulsar-timing array using the Giant Meter Wave Radio Telescope, the Meerkat pulsar-timing array. Meerkat is this array of radio dishes that is sort of a precursor experiment to the square kilometer array. And then newest is the Chinese pulsar-timing array using FAST, the 500-meter aperture spherical telescope, which is bigger than Arecibo ever was, and is really an extraordinary instrument. We're all connected together within the International Pulsar-Timing Array. So within that collaboration, we attempt to fuse our data sets together and improve our detection prospects, because while we monitor some of the same pulsars, they're not all of the same. There are important reasons why we monitor similar pulsars in the sky just for pulsar astronomy purposes. But we also have lots of distinct pulsars in each of these different collaborations. So fast forward and then to 2023, we have most of these collaborations reporting evidence for a gravitational wave background. That is about 3.5 to 4 sigma evidence for a statistically isotropic background of gravitational waves, given correlations between those pulsars that are in good agreement with this Hellings's and Downs curve. And the degree of significance varies in tune with the sensitivity and the number of pulsars monitored of these different collaborations. So Nanograv had about 3.5 to 4 sigma. PPTA and EPTA combined with the Indian pulsar-timing array had lower. The Chinese pulsar-timing array actually reported 4.6 sigma significance, but we're just starting to look at their data now and doing similar detection statistics as we do in our analyses. They use slightly different techniques. So that was the state of the field as of 2023. And then late last year, we had the Meerkat pulsar-timing array come along, and they were monitoring 80 plus millisecond period pulsars almost contemporaneously. So they just started observing the same pulsars and built up this large number of pulsar array over about 4.5 to 5 years. And they got this measure of the correlations between those pulsars. So already, even with 5 years and in this campaign that was essentially constructed in order to be the best way of finding gravitational waves, that is using lots of pulsars to forge many pairs and measure this Hellings's and Downs curve, they were able to get this breakthrough evidence as well. Now, with only 5 years of observations, they can't access the same kinds of astrophysics that the legacy PTA collaborations can, because with only 5 years, you're not pushing deep enough into the lower parts of the gravitational wave spectrum in order to find some of the interesting features of the spectrum itself. Speaking of, the target population in this band is a large population of supermassive binary black holes. That is our expectation. Where these binary black holes should be ubiquitous and a natural byproduct of how galaxies themselves merge and grow over cosmic time, with the resident massive black holes finding each other within the galaxy merger remnant and then forming bound pairs that inspiral and emit gravitational waves. Now, there's a reasonably long delay between the initial galaxy merger and then when the black holes reach tight enough separations to emit gravitational waves in our sensitivity band. Could be of order a gigayear or more. But if it does happen, then it's emitting gravitational waves that we can be sensitive to. And we don't have the resolving power to pick out all of these individual signals individually, because within our band, they're essentially monochromatic, non-evolving signals. So these are massive black hole binary systems that over 15 to 20 years of observations are essentially non-evolving. And so the gravitational wave signal is incredibly simple. It's just a monochromatic wave. But that means that they all stack up incoherently and produce what we model as a stochastic gravitational wave background. Now, the expected characteristic strain spectrum for a population of inspiraling compact objects is relatively simple. It's just a power law that goes as f to the minus 2/3. But in pulsar-timing arrays, we're not directly measuring the gravitational wave strain amplitude. We're measuring timing offsets or residuals caused by those gravitational waves. So you'll occasionally see that transformed into the power spectral density of the timing residuals, which is still a power law and goes as f to the minus 13/3, about 4 1/3. So that's usually our reference power law for the spectrum of gravitational waves produced by these supermassive binary black holes. But there's lots of physics that goes into even the formation and the dynamical evolution of these supermassive black hole binaries, as I'm sure many people in here know. Initially, in the galaxy merger remnant, you've got a period of dynamical friction, which brings the black holes down to about a separation of order tens of parsecs. And once you get down to of order parsec or tens of parsecs, you've got lost cone scattering events, potentially some interaction with circumbinary disks. This is the regime of the so-called final parsec problem, which is not really a problem anymore. The problem is more, what is the combination, what is the set of ingredients needed to actually merge these systems efficiently within a Hubble time. But since there are lots of theoretical mechanisms that can actually overcome this final parsec fueling problem, if we assume that we overcome that and get down to the milliparsec separation stage, then we get to the regime where gravitational wave emission will register in the pulsar-timing array band.
What's the main background to? What are you fighting against in terms of mimicking effects?
That's a good question. So the mimicking effects in this correlation signature, which is that Hellions and Downs curve, it doesn't look exactly the same as global drifts in timing standards. So that can produce just a flat line of correlation because it's present in all of the pulsars. Another possibility is that if we don't precisely measure the position of the solar system barycenter or have efficient models of constructing that, then that will induce a dipolar correlation signature in the pulsars because we have to reference all of our observations back to the solar system barycenter. And in order for that to be a subdominant contribution to the noise or the mimicking effect, we need to know the position of the barycenter to within 100 meters. And there's no NASA use case that has the barycenter known to within 100 meters. And it's only been within the last few years that the addition of Juno data to the ephemeris models have actually made that possible. So it's something that we think is not an effect anymore, or at least the gravitational wave signal seems to be above that baseline. So the way that gravitational wave signals in PTAs would manifest is either as this stochastic gravitational wave background from the superposition of lots of these signals, or we hope as individual massive nearby binaries that are sticking up above the level of that gravitational wave background and are within the reach of us to individually resolve. I've drawn this little extra box here because it's important to point out that we will never be sensitive to the actual oscillatory part of the gravitational wave signal from the binary merger. That is something that will be seen maybe even in between the PTA and the LISA bands for these kinds of massive black holes. So we're not getting the oscillatory part that you see in the LVK reconstructions, but we could be sensitive to the DC offset, the binary merger memory offset, which would just look like a step function in strain to us, but because, again, we're sensitive to timing offsets, that will look like a ramp function that's either positive or negative. It's modulated by the antenna response of the gravitational wave signal. There are some intrinsic pulsar effects that can look like this kind of ramp feature, but the ramp feature appears only to go one way for the intrinsic pulsar noise. Those are called pulsar glitches, where you have a sudden change in the pulsar's rotational period. So an indirect way of accessing the merger event, but we don't get the nice oscillatory part. So how do we go from measuring these gravitational wave signals to actually characterizing the binary population? It's access to the spectrum itself. So we assume that we're measuring the energy density, the fractional energy density in gravitational waves caused by these binary systems. And so we just model this as an integral over the entire binary population and all of the gravitational wave emission coming from each of those binaries. So we can relate back and forth between the energy density or the characteristic strain or that power spectral density of the timing residuals. So the question that we've kind of plagued ourselves with is how do we best model this binary population so that we can connect these models onto our data and infer aspects like the differential merger rate in terms of the mass and the redshift. So I'll get onto that in a second, but I think you had a question.
I think.
Okay, good. So there are a couple of different ways we can try to parameterize this or at least extract some of the astrophysics. Either we attempt to create semi-analytic prescriptions of this integral over the binary population and model it that way, or we just try to get the most agnostic, flexible spectral model, just treating this like a power law or something that might turn over at very low frequencies. We might be interested in modeling the turnover at very low frequencies because that gives us access to those final parsec dynamical processes where the df by dt of the binary system is not really due to gravitational wave emission, but could in fact be lost cone scattering events or interactions with the disk. So we can try that, but we still need to incorporate variance from population discreteness. This integral is kind of a red herring because really we're looking at a Monte Carlo realization of this process, and so we need to build in that we're accessing one realization of this process. So the technique we've settled on is to use emulators, and I'm sure lots of people here are familiar with emulators. The idea that if your population simulation is too expensive to generate many realizations online during your Bayesian inference of your data, then you run a campaign of targeted simulations across the hyperparameter space of your setup, and you stitch those simulations together, that kind of library of simulations together, using some kind of emulator model. So that way you've distilled the important physics down to the observables, and you have something that's fast enough to connect on to your Bayesian analysis. The technique that we've used most recently and in the nanograph 15-year dataset analysis was Gaussian process regression. So Gaussian processes are just used to interpolate across those libraries of simulations, essentially. And they allow you to extrapolate beyond your library space, but it gets very, it gets very poorly in performance once you get outside of that library space. And the results we found from the nanograph 15-year data set are summarized in these 6 panels. So these 6 panels are the 6 different parameters of the binary population that we analyzed with. We started off with a prescription for the galaxy stellar mass function, some normalization for that, and then some characteristic mass. Then we had a way of connecting the galaxy mass function to the mass of black holes. So this is the mean of the bulge relationship, and then some intrinsic scatter. And then this is some phenomenological timescale, kind of dynamical timescale for the binary system in gigayears. This is accounting for the lag between the galaxy merger and then when the binary system gets down to a small enough separation to be in the PTA band. And then finally, some parameter that for all intents and purposes is describing the hardening rate of the binary. So it would have some value for gravitational wave hardening, another value for lost cone scattering, et cetera. In the very light dashed lines, you've got the priors that we put on these various parameters. So either we tried with uniform priors or with astrophysically informed priors. And then in the heavier dashed, you've got the posterior probability distributions that are recovered from our analysis. And let's see, which ones should we focus on? Mostly the characteristic mass from the galaxy stellar mass function is being updated from the prior. The phenomenological timescale that we have no real strong priors on, that is showing a preference for efficient evolution, that is lower dynamical timescales of the order of a few gigayears. So it certainly seems to be tapering off once you get up to a Hubble time. But many other parameters here are actually ill-constrained or just filling their priors. And so we need better models or better ways of characterizing the binary population where we can update our information. And also, these Gaussian processes actually scale poorly with the size of your library. So if you want to go beyond this 6-dimensional space of population properties to a larger space, larger number of hyperparameters, and pin down your emulator with more simulations, then GPRs actually scale very poorly. I'll come back to that in just a minute. Overall, a population of supermassive black hole binaries does seem to be consistent with what the PTA collaborations are observing. In order to do that, we do need higher supermassive black hole masses than expected, at least higher than the mean bulge relationships that we've seen so far in the literature, with relatively short binary lifetimes, less than a few gigayears. So not within the realm of possibility. If we only tweaked one of these parameters higher, then we'd have to take it all the way to the extreme of its prior boundary. But it's enough to relax that on several parameters and just have them be slightly higher than expected. So consistent, but it is trending towards the higher end of previous population models in the literature. This is kind of a summary of different population models over time, over the last, say, 10 to 20 years. And our recovered posterior probability distribution on the amplitude of gravitational waves is towards the high end, still overlapping with those predictions in the literature. But it's interesting, and I think we need to look more at possible noise conflation that could have leaked in and made our amplitude perhaps slightly bigger than expected. If we take these results, then we can ask what kinds of gravitational wave sources are we looking at? What kind of massive black hole binaries are PTAs really accessing in their observations? In the dashed here, you're seeing the underlying distribution of massive black hole binary properties in the universe. So this is total mass, mass ratio, initial redshift, and then a final redshift at which they would merge. In the color bar here, you've got the frequencies, the gravitational wave frequencies at which these sources would lie in the PTA band. And then in the solid, you're seeing that underlying distribution of massive black hole binary properties convolved with our detector selection effects, which essentially means that we're sensitive to the most massive black hole binaries in the universe, the really gigantic systems that are way into the tail of the massive black hole mass function. We're favoring mass ratios which are closer towards 1. That gives us a stronger gravitational wave signal when they're equal mass. And they're relatively nearby systems as well. So the typical source that might be in the PTA band that we're actually sensitive to and dominates that gravitational wave background signal is of order 10 to the 9, 10 to the 9.5, favoring mass ratios that are equal, and then redshift certainly closer than 1. So this is a relatively local view of the massive black hole landscape. Going back then to how we can go beyond Gaussian process regression of these supermassive black hole binary populations, it's really, really important to model and account for population discreteness. Population discreteness can, at higher frequencies in our band, lead to spectral excursions away from just an expected power law. And if you just try to fit those spectral excursions, you might be biased in your inference and think you've got properties that are, on average, not what you have. So we need to account for that population discreteness at higher frequencies. That's where the spectral excursions actually manifest most, because at higher frequencies, the binaries are spending less time in each frequency resolution bin. And that means that, on average, the number of sources in those bins is smaller. So you get these Poisson effects at higher frequencies. This is something we've characterized relatively recently. This is one of my students, William Lamb, who in a letter last year characterized the moments of the ensemble distribution of gravitational waves at different frequencies. And he's got a new paper coming out that is Astrophysical Gravitational Wave Backgrounds Are Not Normal. That's a bit of a pun that he came up with, because they're certainly not. At low frequencies, they're reasonably normal. But as you get towards higher frequencies, the higher moments in the distribution really kick in and could lead to some of these spectral excursions that would bias you if you didn't take them into account. Moreover, we can just abandon the idea of Gaussian process regression as our emulator and go to something like a normalizing flow. So our normalizing flow is one of these deep neural network techniques that allows you to efficiently map between your data and the astrophysics of the population. It scales very well with the training size of the libraries, and it also can allow you to access larger numbers of hyperparameters when you build your emulator. So this is something that we've constructed recently. This is by a postdoc, Nima Lal, who's in my group. And we've just used the same library of simulations that were used in the nanograv analysis, but we've switched from a Gaussian process to a normalizing flow emulator. And the performance into the tail of the distributions, where the spectral excursions might be most prominent, are recovering the library simulations very, very well. Much better than a Gaussian process that, of course, is just going to model this entire spread as a Gaussian, so will not track the ensemble distribution very well. In fact, Nima Lal used this normalizing flow emulator recently to try to understand what PTAs can actually say about the binary population and try to get a feel for whether there are some parameters that are just very ill-constrained and that we will never be able to make reasonable inferences of. So he's done lots and lots of realizations of idealized and realistic PTA data sets. And in here, he's got the 6 different parameters that were shown in the previous plot for the nanograv recovery. So these are all the astrophysical parameters. And then he's recovered the Bayesian credible regions and ranked all of these points by the uncertainty on the dynamical timescale parameter. So each of these points here should be tracked across the 6 different panels, but they're all ranked by their order in this plot here. He was able to do this efficiently because we've embedded this normalizing flow emulator into a new GPU analysis pipeline that we've recently built that allows us to do these large-scale analyses in order hours instead of order weeks or months. What he's found is that some parameters are just unconstrained by PTA data, even for highly idealized observations. But the best prospects for updating our prior information about the binary population parameters are these binary lifetime parameters, the binary hardening rate, which is this new parameter, and then the galaxy stellar mass function characteristic mass. So it's not that we don't get any information beyond the prior from the other parameters, it's just that they tend to lag behind the inference of these lifetime hardening rate and galaxy stellar mass function parameters. So perhaps we should just incorporate the knowledge that we have from electromagnetic observations, put stronger priors in those other parameters, and treat this as one big population multi-messenger astrophysics problem where we've got informed priors and then some parameters that we just can't access with electromagnetic observations, like the hardening rate and this dynamical timescale parameter. Any questions? Because I'm going to do a bit of a segue now into individual sources. Do you have a question?
What's the y-axis?
The y-axis is the value of the different astrophysical parameters. And then the x-axis is just the particular simulated data set. So it's the index of the simulated data set. Oh, you mean this y-axis? This one here?
Yeah, and you have a bar.
Yeah, the bar is representing the prior distribution. That's a good question. I should have said that. So this gray region is representing the prior distribution on those parameters. For this dynamical timescale parameter, we have essentially no constraints put on it in this analysis. We have weaker constraints on the other parameters. And we're trying to determine which parameters we have the best prospects in order to update their prior information. And these are the ones that we can best access, which are binary lifetime or dynamical timescale, this hardening parameter, and then the characteristic mass of the galaxy stellar mass function. The other parameters, even in idealized scenarios, are not being updated from their prior very much. Yeah.
So when you're talking about electromagnetic observations, do you also mean observing some stochastic background or focusing on some kind of known binary candidates, or what kind of observations?
It's more taking what we know about massive black holes in galaxies and what we know about large-scale samples of galaxies themselves in order to pin down other properties of the galaxy stellar mass function, the bulge distribution or M-sigma relation, et cetera. Why not just put those as informed priors on these parameters when we do our gravitational wave analyses so that we have the best prospects of updating things that we don't know about already, or we have ill-constrained parameters already, like these, which in the binary dynamical timescale at small separations and this hardening rate are sort of happening in the dark at the moment. And so that's what gravitational waves can help you with. So it's sort of like population multi-messenger astrophysics.
But not just focusing on observing like known binary candidates.
No, I'll get onto the known binary candidates later, but this is a more population idea. Okay. So let's go beyond the background, because the ultimate goal, if we've got an astrophysically sourced gravitational wave background, is to fragment it into a number of massive black hole binaries sitting atop some underlying stochastic gravitational wave background. And there are a number of important questions there that pop out. when you try to do this. First of all, how do we localize these binaries? What are the important effects in a pulsar timing array experiment that dictate how well you can localize these gravitational wave signals? As I'm sure many people know here, gravitational wave detectors are terrible at localization. And so you need to pull as many tricks as you can to localize them well in the sky. I'll talk about it later, but this is a signal to noise ratio of 8. So that would be a threshold event for us, but it's still quite a large patch on the sky. Then how do we pin these gravitational wave signals to plausible host galaxies? We have some help here because these are the most massive black hole binaries in the universe, so they're most likely to reside in the most massive galaxies in the universe. So we have, in some ways, an easier problem than in LVK or maybe even in LISA, where you have to take into account many more different effects. And then finally, I want to talk about how we localize these binaries on the sky, because it's a tug of war essentially between the proximity of the gravitational wave signal to the pulsars in the sky, and then what I've called here pulsar term effects. I'll explain the pulsar term in just a second. So as a brief aside, the apparent change in the rotational period of a pulsar due to gravitational wave effects is given by the integral over the entire photon path that these pulses are taking of the difference in the metric perturbation between subsequent pulses. So if we take this path integral over the difference in the metric perturbation at subsequent pulses, and we make some approximations that the pulsar period is much, much smaller than the gravitational wave period. That is an excellent approximation because these are milliseconds, these are years or decades. We get down to a smaller form where the fractional change in the apparent pulsar rotational period depends on some projection factors. This vector P is the unit vector pointing to the pulsar. And then this path integral again, but it now reduces down to the leading order term and a Taylor expansion of the metric perturbation.
Know how to do this path integral across, I mean, what do you?
We're making very, very simplistic assumptions here that it's just an unperturbed photon path. And these are only timing effects that we're picking up. And we're not taking into account any intervening matter or anything like that at this stage. So it's a very approximate form, but it's a good approximation given this very different change of scales in the pulsar period and the gravitational wave period. That gets us down to Z, which is the delta P over P from the previous slide. That's the redshift, the apparent redshift to the arrival rate of these radio pulses. And it splits into some angular projection factors. This is actually going to be very close to the gravitational wave antenna response, where this is the unit vector pointing to the pulsar. This is the direction of gravitational wave propagation. And then this is the difference in the metric perturbation at the Earth and the metric perturbation at the pulsar. But importantly, it's the metric perturbation evaluated at some lag time behind the Earth term. So this is the metric perturbation now, and all of the pulsars will share that common phase of that Earth term. But this pulsar term is sort of an imprint or a snapshot of the dynamical time, potentially thousands of years ago, but it's the light travel time back to the pulsar that is imprinted in our gravitational wave observations in the timing residuals. Yeah.
Sorry, what's Z?
Z is the apparent redshift or Doppler shift to the arrival rate of the pulses. So in a cartoon form, what we've got here is gravitational wave propagating into our system. Here's that unit vector pointing to the pulsars. Then we've got pulses propagating through that perturbed space-time. And the net effect, once we do that integral in the previous slide, is we get left with a pulsar term, so the jiggling or the metric perturbation at the pulsar, and the Earth term. But like I said, the potential lag time between those different influences depends on the distance to the pulsar and some angular projection factors. But these distances are of order kiloparsecs. So that lag time in these two different imprints, the pulsar term and the Earth term, could be of order hundreds or 1,000 years. So even though we're looking at gravitational wave signals for decades, and we're not seeing much evolution during those decades, what we effectively get is an imprint of the gravitational wave state thousands of years before. In imprinted in the timing residuals in each pulsar. And if we can stitch all of those together, we could, in principle, measure the chirping of the system over thousands of years. In order to do that, we really need to measure the distances to pulsars exceptionally well. We need to know the distances to pulsars to within a gravitational wavelength, which is of order a parsec. And we have only a few pulsars that we can say that about at the moment. So in a search for these individual sources, you would have the same kinds of parameters that LIGO searches for when it looks at black hole binary coalescences. Different binary properties, masses, frequency, maybe some eccentricity. Spin is not very important for us. The spin effects this early in the in-spiral of the system are quite small. So mostly in our searches, we've got 8 parameters. The 8 parameters that LIGO would put in its most default model for a binary black hole in-spiral. But if we want to include those pulsar term effects that require us to know the pulsar distances well, we better search over those pulsar distances. We don't know them well enough, so we need to make them part of our Bayesian analysis. So we have to search over the pulsar distances and a reference phase angle of that pulsar term in each individual pulsar. And hopefully you can see that bloats our analysis from 8 parameters up to 2n pulsar plus 8 parameters. This makes it a very expensive search. The search for individual sources in PTA data is our most expensive type of search. A gravitational wave background search is really just the noise in the individual pulsars plus a few parameters to describe the spectrum. For an individual source, though, it's the noise in the individual pulsars plus the background, because we have to characterize that as well, plus 2n pulsar parameters for these distances and phases, and then the binary properties themselves. So very expensive and very challenging. But if we can access it, then we get access to a very rich waveform. So this might be, this is the modified Julian date. So this is of order a decade or so. And this is typical TOA delay for, I think this was an order 10 to the 9 chirp mass, 10 to the 9 solar mass chirp mass binary. The cyan here is the Earth term. So that's this monochromatic gravitational wave signal from the metric perturbation at the Earth. But then if you fold in the pulsar term as well, the overall signal is given by this red line here. That's because you've got a lower frequency envelope from the pulsar term. The pulsar term is of order 1,000 years in the past. The gravitational wave emission has been causing the evolution of the binary all throughout that time. So you're seeing the chirping effect here, the lower frequency pulsar term, and then the later higher frequency Earth term. And we just assume a kind of baseline order that we've got gravitational wave emission dominating the evolution of the binary. So what about localization? Can we use any of these effects? The fact that the pulsar term is very sensitive, not just to the pulsar distance, but also the projection factors. Can we use that for localization? The answer is hopefully. In principle, we can. What you've got here on the left is a representation of the antenna response pattern of a particular gravitational wave source. Over here with pulsars being moved around at different separation angles from that gravitational wave source. If you've got very little evolution of the binary over that 100 or 1,000 years, then the Earth term antenna response interferes with the pulsar term antenna response, and you get these sharp fringes. And the width of these fringes are inversely proportional to the gravitational wave frequency and the distance to the pulsars. So your localization of the signal on the sky could be restricted to just one of these fringes if you know those pulsar distances well. This has been called operating the PTA like a diffraction-limited imaging telescope, and is a really exciting prospect if we can get much better distance precisions. Because then you're just limiting the gravitational wave position on the sky to within some small, certainly sub-degree squared angle. But we don't have many of these pulsars for which we know the distance well, and so you just rely on the antenna response gradient information from the Earth term. So if you don't know those distances well, you just try to use the antenna response information to get you into the right region of the sky. So for example, if these are 4 different pulsars and they're lit up by how they're responding to a gravitational wave signal, where the black here is negative and the yellow is positive, Does anyone want to take a low stakes guess for where the gravitational wave is coming from? Yeah, I see pointing. Right. It's right in the middle there. So it's a purely geometric, taking the shape of the antenna response function and using that to localize where you're coming from in the sky. I had a graduate student that was investigating this last year and also developing ranking protocols for how we would take galaxy catalog information, take gravitational wave localization information, and filter out galaxies that were not consistent with the gravitational wave signal. And this is an effort to try to understand how we can reduce the number of plausible galaxies in a localization area down to something more manageable for dedicated follow-up. But what she found in that analysis is that even for fixed signal-to-noise ratio, the localization area of the gravitational wave signal depends on the proximity to the pulsars in the sky. So even if you fix the signal-to-noise ratio, it seems like the signal-to-noise ratio is not the only important factor to consider when you're looking at the area of that sky patch. What's more, the pulsar term, if you incorporate that information, seems to buy you a factor of 2 if you're quasi using the pulsar term information. So this is only if you use the Earth term information. And in the Earth term information, there's no benefit from going higher in chirp mass if you're calibrating the signal to noise to say the same. But if you increase the chirp mass, you're causing the amplitude of the pulsar term to chirp as well. So you're getting this information from the pulsar term is not from the phase evolution of the pulsar term, it's from the amplitude chirping of the pulsar term. And that buys you of order a factor of 2 when you ramp up the chirp mass from order 9 to 9.5. So to lead in order, it seems like the signal to noise ratio and the pulsar source proximity dominate for the regime of single source searches that we can access at the moment. So this got me excited and interested to play around with some calculations myself. And so earlier this year, I decided to construct my dream, which is a ring array. This is if we had a gravitational wave source here and we could just, with the power of theoretical simulation, just construct a pulsar timing array around the gravitational wave source. This is important because this way we can keep the angular proximity of all of the pulsars to the source the same. Yes?
Why not the antipodal point?
You can, yeah, I'm going to vary the angular separation offset here. I'm not going to keep it like that. I'm not crazy, but I have constructed this highly unrealistic ring array. What I did was I did lots of Fisher experiments just to get an idea for what's physically driving the localization. So with this particular ring array and a signal to noise of 10, this gives you the localization patch on the sky if you're only using the antenna response gradient information. But if I do what you suggest and increase the angular radius of my ring array, do I find something interesting in that behavior? So here I'm keeping the signal to noise constant, but I'm increasing the radius of my ring array and then looking at the area of that sky patch. And it seems like you've got a pretty decent power law here for the delta omega, the area of that sky patch, as a function of the ring radius, at least up to of order, a few tens of degrees offset. And so that was just numerical, but I started exploring this analytically as well. And you can break down the sky portion of the Fisher information matrix to a portion that just depends on the signal to noise squared, and then a portion that just depends on the product of antenna response gradients on the sky. And overall, this reduces down to something that is of order signal to noise squared divided by the angular proximity of the pulsars squared. This is an approximate form when you're relatively nearby the source on the sky. But the more complete form is actually this. Just for completeness, this gives you the information, but really it's of order 1 over the angular proximity squared. And so if you were to construct a proxy or an approximate scaling relationship for the localization of signals on the sky with PTAs, you would get that localization area is roughly an inverse sum of the proximity, the squared proximity weighted signal to noise squared. So it's signal to noise squared divided by angular proximity squared, summed over all of the pulsars, and then your delta omega, your area of your localization sky patch, is the inverse of that. And let's break our assumption of a ring array and go to something slightly more realistic, to say an isotropic pulsar array. If I draw many, many different experiments that have pulsars between 10 and 500 in number, and then they all have different heterogeneous noise properties, and I just draw lots of different types of binaries oriented many different ways, and do my Fisher experiments, what do I get? Well, I get that the delta omega actually tracks my approximate scaling relationship for the localization of that signal in the sky very well, at least is good enough to be called an approximate scaling relationship if you were trying to tune your pulsar timing array to get the best localization prospects to sources in certain patches in the sky. I know I'm down to the last few minutes here, so I think I'll skip over, well, I'll say that we do need better pulsar distances. There are lots of different techniques with which we can obtain those pulsar distances, but we need dedicated VLBI campaigns or other ways of getting highly accurate pulsar distances. Then briefly, it's not just coherent templated searches for the signals, the supermassive black hole binary signals that we can attempt, but also coarser anisotropy mapping techniques. That is, we try to look for hotspots in the sky that would be indicative of where individual sources are eventually going to be resolved. So you might imagine that there are below threshold, these hotspots do not show much evidence for a template gravitational wave signal, but it is a hotspot of gravitational wave power at a certain frequency. So could we treat it like that and get an early heads up of where these individual sources are going to appear? In principle, yes, you can use various different anisotropy mapping techniques, either spherical harmonics or individual pixels to try to model these hotspots of gravitational wave power. So could they show up first in intensity mapping experiments or intensity mapping searches rather than these individual template searches? And this is what I had one of my graduate students investigate. This is by Levi Schult. And what Levi found is that even if we have a highly tuned model for the anisotropy, that is what we call a spike pixel model. It's a single frequency, single pixel on the sky search for a hotspot of power caused by an individual binary. The templated search still beats it in terms of the growth of Bayes factor over time and signal to noise. So even though this spike pixel model has only a few parameters compared to the huge number of parameters I told you about for individual template searches, the Bayes factor for the individual template searches and the associated phase information wins out and beats this anisotropy model. So it's likely that anisotropy will give you proposal or other kind of guiding information for where the sources are coming from, but it will not be the means by which we detect individual sources first. This set of experiments we did also gave us some milestones for binary characterization, where, as you might imagine, we only constrain the mass, the chirp mass of the source for the highest frequency injections. So we did 4 different injections here, depending on where the source is injected on the sky. So this is A and B. And then we did a low frequency, 5 nanohertz injection, and then a higher frequency, 20 nanohertz injection. We only get mass information, which is the cyan line here, for the higher frequency source. That's because it has the strongest evolution between the Earth term and the pulsar term. So we can actually use that chirping information to infer the source. But we need of order signal to noise 10 in order to get 50% precision on most of these parameters. And it seems like the frequency and the localization information are the parameters that come first when you're characterizing the binary. I'll just skip over this. So briefly then, onto the targeted searches and the idea that we have candidate supermassive black hole binaries already. Can we lock onto those and do some sort of multi-messenger analyses? So there are different signatures of EM activity that we could track or fold into our ranking of the different galaxies as potential hosts of mergers. You've got large-scale disturbances, but those are likely to die down quite a bit by the time the source has evolved to small separations when we can measure them. You've got offset broadline regions where people look at the radial velocity curves of the broadline region and try to infer for wider separation binaries that you've got, you do have a binary in there, or potentially photometric variability in the central regions of quasars may be caused by circumbinary disk emission. And for many of the candidates that people see in long time scale tracking, photometric tracking of candidates, it's either related to potential hydrodynamic variability of accretion onto the massive black holes, or relativistic Doppler boosting of light coming from mini disks around the individual black holes, or potentially it's a single AGN. It's most likely to be a single AGN with intrinsic photometric variability. So most of the candidates so far, in my opinion, are likely to be individual black holes with some poorly constrained model of the intrinsic AGN variability. But we do have lots of these candidates, so can we just go after them with PTA data searches? Can we assess whether there are gravitational waves coming from those candidates? We constructed recently a multi-messenger PTA search for individual binaries because the gravitational wave information coming from a binary and the electromagnetic information are mapping the orbital dynamics and characteristics in different ways. So if you had a typical gravitational wave signal coming from a binary, and you had a typical Doppler boosting, relativistic Doppler boosting signal from a system like this with gas accreting onto the massive black holes, it would co-evolve and the phase evolution should stay coherently connected across the gravitational wave and EM signals. So this would be the sinusoidal relativistic Doppler boosting signal. This would be some kind of gravitational self-lensing effect of radiation coming from each of these black holes lensed by the other. And then this is your basic gravitational wave signal where the frequency is twice the orbital frequency of the binary. So very recently, Maria Carisi, who's now faculty at Washington State and at Forth in Crete, constructed this multi-messenger Bayesian analysis where the gravitational wave only posterior for this particular experiment is given in orange. The EM only, that is modeling the characteristics of the binary just in the relativistic Doppler boosting, gives you the green. In the gray, this is what you'd get if you took your EM model and you constructed one-dimensional priors on the different parameters and just put those one-dimensional priors onto your gravitational wave search. That's good, but you're losing some information from the covariance between those parameters in the EM analysis. So why not just do everything at the same time? Do a complete multi-messenger joint likelihood analysis, which is what you get in the purple here. And what I'm trying to say is that they're mapping the orbital dynamics in different complementary and sometimes orthogonal ways, because the size of the posterior compared to the EM and the gravitational wave single messenger analyses, it's much smaller. So multi-messenger analyses could be a very effective way of pinning down the parameters of a binary or refuting or validating the presence of a binary in some of these candidates. We also did a targeted analysis for various different candidates that are in CRTS and other different time domain surveys. We don't have evidence of any gravitational wave signals coming from those candidates yet. The PTA data is not sensitive enough yet. But we have set these important benchmarks for how to go about that kind of candidate validation. And that was led by our colleague at Yale, Chiara Mingarelli. So finally, the road ahead is that we have this initial gravitational wave background evidence. We're going through ever more refined estimates of the spectrum and the astrophysics of the population. Then in the near future, we should have good prospects for finding individual binaries, maybe even multi-messenger binaries, until we get a complete view of the population from the individual sources and the stochastic background. That'll be facilitated by new radio instruments like the Deep Synoptic Array 2000, which is led out of Caltech and Schmidt Sciences, the Vera Rubin Observatory, giving many, many more different candidates, and then in the future, NGVLA and LISA. I couldn't be here and not give a quick overview of LISA in one slide or two slides, but LISA will have lots of different sources. It really is the best instrument for the entire zoo of different gravitational wave sources that we think are out there. It inherits sources from both LVK and PTAs, but it's also got its own individual events too. And as you can see here, well, the constellation of satellites is large enough that you could fit the entire sun inside. So it's a larger scale gravitational wave experiment in the solar system due for launch in 2035, which will also have not just the in-spiral, but the coalescence and ring down of massive black hole systems. So I think I'll leave you all here with some takeaways that we're constraining supermassive black hole binaries in a population sense from the background, and also in the near future with individual events that are potentially multi-messenger as well. All right, thanks very much.
That's only got time for questions, but yeah, he's here the rest of the day. Sasha?
Yeah, so when talking about multi-messenger searches, you mostly talk about constraining the parameters of the binary with gravitational waves and multi-messenger and electromagnetic. But we have maybe a few seemingly convincing candidates where the periods and maybe even the masses are reasonably well constrained, but we cannot confirm for sure that they are binaries. Is there a way to kind of like just look at the few points and say, okay, just yes or no, basically, given the periods, masses, and everything?
Yeah, I would say one of the first successes of pulsar-timing array experiments was looking at a potential binary system in a radio galaxy that was 3C66b. 3C66b had a variability in its light curve that was of order 1.05 years or something like that, and it was such a high variability, such a high amplitude variability that PTAs would have seen it so clearly. Like you could have seen the gravitational wave signal in the timing residuals. So we were able to use PTA data at the time, this was more than 20 years ago, to constrain the presence of a binary.
So basically, constrain, you mean rule out or?
Invalidate a lot of the parameter space for a binary system. You can squeak by and there might still be some potential for a binary if it's highly eccentric. But that system for us now is a useful test bed for new techniques. We don't really think there's a binary there.
Thanks for a very nice talk. I was very curious. So there could be a huge gain, right? If you just found many more pulsars. So as a factor of 2, like how does that sort of translate in terms of detection?
Yeah, the signal to noise of the background scales roughly linearly with the number of pulsars. And for something like DSA 2000, DSA 2000 should allow us to regularly monitor up to 200 millisecond pulsars. Going from the nanograv current observations, which in our recent data set were of order 70, and our newest data set, which will be 20 years long, it'll be of order 80. This will be a significant gain for us. And also it'll pepper the sky with more pulsars to improve our localization precision of any individual sources as well.
So with individual sources, has OJ287 we looked at? Thank you for asking.
Yeah, that's a good question. It's a little bit far away for us to be able to comment on, but it is something where we always put OJ287 on our maps of candidates. So we've not been able to do targeted searches because for us it's just beyond our horizon.
But why is it beyond the horizon? It has a redshift that seems to fit pretty well in your redshift range.
I think it's the revised mass is too small. Yeah.
So that's
Right. That's a good point. Yeah. So that killed the chirp mass. Yeah.
But there are pulsars around there.
There are pulsars around there. I think, unfortunately, the gain from having pulsars around there is not enough to overcome the fact that it would be just a weak signal for us.
Hi, yeah, very nice talk. You said at some point that a redshift 1 band would seem to be above the local scaling relations with the bulge mass. Do we know by how much?
So my comment there was, in order for our observed gravitational wave background signal to be consistent with a population of supermassive binary black holes, that the normalization of the MM bulge relationship, I think it lies above the standard relationships like McConnell and Ma, and other relationships like that. So I can show you the plot. I can't comment exactly on how far above that curve it is. But it's raised a lot of questions. There were some papers by Gabby Sato-Polito and collaborators at Princeton on whether the amplitude of the gravitational wave background is just too big, and what that implies about the typical mass of black holes in our local universe. And according to their calculations, it was order 10 to the 10, a few times 10 to the 10, gigantic systems. But there's been some further work last year on kind of squaring the galaxy stellar mass function with massive galaxies in the massive survey. This was from Chungpei Ma and Emmy Leopold at Berkeley. And they constructed a new galaxy stellar mass function that was consistent with the massive survey. And if you follow through the calculations, you get a strain amplitude that is actually consistent with the PTA result. So there's a lot of back and forth, I think, at the moment. From a data analysis perspective, I think some noise is leaking into our gravitational wave sector. And I honestly think in the next few years, we'll introduce more customized and advanced noise models for the pulsars. And then the amplitude will just relax ever so slightly. It doesn't have to be even a factor of 2, but it will go down enough that any tensions will disappear.
Right, so when every pulsar has a tailored noise model.
Yeah.
right?
Yeah, at the moment, every pulsar is its own kind of special snowflake. And we treat them all the same at the moment. We just give them basic intrinsic rotational instability models and very basic models for the interstellar medium noise. But really, there's lots of really interesting physics going on in there, and they have to be treated on a one-by-one basis.
Is there a smoking gun signal that would convince you that you were seeing an individual binary? I mean, what would be what's the sort of high end, like first LIGO booming signal that everybody said, that's a binary?
Yeah, so there's no good community answer at the moment. I think that's something we're trying to develop because we need detection protocols for this kind of thing. And it's different from LVK because LVK got very lucky with a signal to noise of order 30, and ours will just be creeping past signal to noise threshold. I think it won't just be gravitational waves. I think gravitational waves by themselves would be unconvincing.
I want a multi-messenger.
I want a multi-messenger event. I think that would be a home run for saying that there's a binary there. In whatever form, photometric variability, maybe some really, really high precision VLBI or something, I don't know.
I have a question, and there's also one question on Zoom, so maybe I'll just ask the Zoom question. So Colin Burke asks, will Lisa be able to inform the PTA noise models or results at all? Or are the different frequency ranges too different?
They're rather different. People have attempted to make this connection of the massive black hole binary population across these decades in frequency. Here, LISA is sensitive to of order 10 to the 4 to 10 to the 7 solar mass binaries. PTAs are sensitive to 10 to the 8 to 10 to the 10. That's still a pretty big gulf, and there's a lot of flexibility in the mass function of the black holes that any PTA constraints that we currently have are not really updating our expectations for the LISA merger rate that well. So I think it's possible, but it's a very weak connection at the moment.
There are no other questions.
Can I ask my question?
Oh, I mean, sure, go ahead.
My question was slightly open-ended. So I remember when the news of some of this PTA results came out, there was speculation about informing sort of cosmic strings and so on. Has the spectral characterizations that you talked about, have they ruled those out by now?
Oh, let's see. I always carry some backup slides. Let's see. Yeah, so what you're talking about is probably, this is a nice way of visualizing the connections that different papers have to a paper. And so astrophysics and massive black holes are all up here, but we got a ton of attention from theory. And we had a very extensive search for new physics in our data set as well. The constraints are very weak at the moment. On the left, the gray kind of vertical violins are the recovered PTA spectral values. And then in the other kind of colored regions, those are sensitivity regions of different gravitational wave experiments. So we did searches for or constraints on primordial gravitational waves, phase transitions, cosmic strings, superstrings, domain walls. There's very little we can say at the moment. There are no strong constraints. The strongest constraints appear to be on stable cosmic strings, I think, where the predicted spectrum is quite different in shape from what we've seen in our constraints. And we did searches for things like ultralight dark matter as well, because that would induce a time-dependent gravitational potential that affects our pulsar timing observations. At the time, this was 2 years ago, we were performing torsion balance experiments and some atomic clock tests, but optical lattice clocks are getting incredibly accurate, and so have outstripped our constraints. So it's on our mind, and we have a team of people that are dedicated to doing this kind of analysis. But it's not the likeliest of sources.
Okay. There's another question on Zoom, but you can decide.
I think people should probably go to lunch.
Yeah, maybe it's
All right,
Yeah.
maybe it's time to call it. Thanks, Stephen, again.
Thank you.